My name is Laura. I'm a PhD student studying applied math at York University. My PhD is on math modelling of lithium-ion batteries, like this kind of battery that you would probably find in your cell phones or in your laptop. But in addition to battery problems, I also get to work on other interesting problems like the flu, COVID-19, and groundwater flow problems, which are about the water that flows under the ground. So I know for a lot of people, usually some of the first things that come to mind when you think of math are theorems and proofs or solving an equation to find x. And yes, these are part of math, but there's so much more. Math modeling is the process of using mathematics to describe some real-world problem and then using different skills and techniques to study different parts of the problem or to make predictions. So I'm going to tell you a little bit about some of the problems that I've worked on using math modeling techniques. Which brings me to the title of my talk. What do the flu, batteries, and groundwater all have in common? So in batteries, like these batteries, they're known as lithium-ion batteries, which means that there's lithium moving around inside the battery. In groundwater, we have water moving under the ground. And for the flu, we know that this spreads due to the movement of people. So while these three problems are quite different, they all have similarities in the sense that an important part of the problem involves movement of some big part of the problem. And in all three cases, we can use mathematics to help us investigate the research questions, streamline testing processes, and make predictions. So the first problem I'm going to talk to you about is the battery problem. So have you ever picked up your phone to see that you had low battery and thought, what, again? Didn't I just charge this last night? When you first got the phone, the battery seemed to last very long. But then after a couple of months, you found that you had to charge your phone every day, if not even more often. So why is this? Why does the battery seem to get worse over time? Is there a way we can improve the battery? Imagine if our phones could last 1 week, 1 month, even 1 year. Wouldn't that be amazing? So these questions are becoming even more important now because of climate change. In an effort to combat climate change, we're looking for more sustainable and environmentally friendly energy sources. Rechargeable batteries like lithium-ion batteries are becoming really popular and are expected to power technologies of the future, like electric vehicles. But in order for this to happen, we need to have confidence that our batteries are going to last long enough to do the job they're supposed to do. So how can we fix this? This is one of the greatest problems affecting batteries at the moment, the fact that they die faster over time. And this is what I am working on. I'm using math to help investigate why the battery fades over time and looking at different ways that we can improve this. So as I mentioned, these batteries that are in our cell phones and our laptops are known as lithium-ion batteries. So there's stuff called lithium inside. And when you use your phone, the energy to power all your applications comes from chemical reactions that happen inside the battery. So here, this blue stuff on the right-hand side is lithium. And when your phone is fully charged, all the lithium is on one side of the battery like this. Then when you use your phone, the lithium starts to move to the other side of the battery. And as the lithium is moving, this movement is causing chemical reactions which generate the energy needed to power your phone. When all the lithium gets to the other side, your phone dies. So we charge our phone, which is sending more energy into the battery and pushes the lithium back to the first side and back to 100% battery. But the problem is that not all of the lithium always makes it back. Sometimes some lithium gets stuck along the way like this. And over time, the more we use our phone, more and more lithium can get stuck, and this means there's going to be less lithium free to move from one side to the other. And this is why our phone dies faster. So I'm using math modeling to look at how and why the lithium gets stuck like this. And also, what can we do to stop it getting stuck, or at least to have less lithium getting stuck? And as I said, this is becoming extremely important. this is the biggest problem affecting battery life and storage times. So a lot of people are interested in trying to improve batteries and their lifespan. So can you imagine a chemical engineer wanting to test a new battery material to see if it helps reduce this issue? So they might make a new battery, and when they're doing that, they'll have the new material at one point of the battery, run some tests to see how good the battery does, and then maybe never use it again. And then they're going to have to do this again for any other materials they want to test. So like if you want to test a lot of different materials to see what works best in the battery, this is going to take a lot of time and could be really expensive. This is where math comes in. As a mathematician, I can make a model to replicate the battery, and I can make it as realistic as possible by comparing with experiments that the engineers have done, and then we can use different parameters from their experiments to make it realistic and lifelike. When we want to test a new battery material, then instead of building a new battery or building a new model, we can make small changes to the model we've already made and then test the battery this way. So this is how math is almost like X-ray vision, looking inside the battery and telling us what's going to happen. And also looking into the future, because we don't actually have to build the battery. We can use our model to see if it will be a good material to use in the battery. And then if it's good, we know we could go further with it and actually make these batteries. And if not, we already know that we don't need to waste the time and money. So overall, math is a great tool to model the battery and the different metals and materials that could make the battery last longer over time. But another problem where math can be helpful in the testing process is in the problem relating to groundwater flow. So suppose you're watering your plants or spraying weed killer on your garden at home. You spray these fertilizers or weed killers on the ground, and they have some job to do, like helping the plants to grow or killing the weeds. These sprays have chemicals in them, and these chemicals will travel through the soil and will be absorbed by the plants or eaten by bugs in the soil. So I have a diagram here, I hope you can see it, to help explain what's going on. So here we have the ground, and on top we have a tree and some plants, and then we have all our soil and then the water under the surface. So we spray on the chemicals and they travel through the soil. But the problem is, how do we know how much spray to use? So imagine you're watering your plant at home. If you use too little water, the roots are going to soak up the water really quickly, and not all the roots are going to get as much as they need. So you might start to see your plant die a little bit over time. But if you use too much water, the roots can't take it all in, and so you might even see some water floating on the top of your soil. The same thing can happen in this groundwater problem. But here, if you spray too much chemical on the surface, the chemical might make its way down through all the soil to the underground water supply, which we don't want to happen, because then it could get into people's drinking water or into lakes and streams and could affect the wildlife there, like the fish. So how do we know how much to use? We could go and dig samples of the soil and test them, but again, this is going to take a lot of time and could be really expensive. So again, math comes in to streamline the testing process. So in a project that I worked on, we used different approaches to study how the chemical travels through the soil, and we were able to model different factors that affect how this chemical degrades over time by looking at how sunny it is, how much rain there is, and even what type of chemicals there are and what kind of reactions are happening between the chemicals and even in the soil. So then we were able to use this model to figure out, if we spray this much, how much is going to get down to the water supply, and could then figure out how much chemical we should use. So overall, the testing process is greatly reduced, because if we find from our model that there's going to be too much chemical, we can say, okay, we either need to spray less Or if we're really concerned, we could go and test a sample just to check. But the point is, we either don't need to do the physical testing, or we've streamlined the process of the physical testing by only testing the places that we're most worried about. Okay. And so those are two different places where math can be used, like X-ray vision, seeing what's happening in the battery or under the ground and telling us what's going to happen in the future. Another place where math can help us figure out what's going to happen in the future is in virus modeling. So, for example, the flu or COVID-19. So we know that these viruses can spread through the movement of people. Someone can get sick if they come into contact with someone who is already sick. So what we can do is we can build models to find out how quickly the virus will spread by considering the movement between people and how likely it is to come into contact with someone who is sick. Sometimes these models can be really simple and can be based on information from the past 2 weeks, for example. So if we know how many people got sick each day over the last 2 weeks, we can use this and some mathematical tools to figure out how fast the virus is spreading and therefore how many people will get sick over the next 2 weeks. So I have a little example of this. And if the writing is backwards, it's okay, I can explain what's happening. So on the x-axis here, we have the day number. So we have day 0, day 14, and day 28. And on the y-axis, we have the number of people who've gotten sick. So we know over the first 14 days how many people have got the flu or COVID-19. We then use this information and our mathematical model to figure out how many people will get the flu over the next 14 days. So this is what we come up with. And we want to know how good our model is. So is this how many people actually get sick, or is it not? So once the 14 days have passed, we can look at the real data of how many people have gotten the flu over that time and compare with our model. So here, the green line is the model prediction and the pink line is the actual data. So we can see that they don't match exactly, but the model does a pretty good job of giving us an idea of how many people would get sick over those days. And we can always make these models more complicated. For example, if we wanted to figure out when the variants of COVID are going to become a bigger problem than the original strain of the virus, or if we wanted to find out which strain of the flu we need to prepare for in the next flu season. Other work that we can do with these type of models for virus modeling is looking at how good the interventions are at stopping the spread of the virus, or how immune are we after the vaccinations. So I know that I've covered quite a lot of different ideas here, but I just wanted to give you an idea of how mathematics can be a really powerful tool for helping us to solve everyday problems. And also, how cool is it that we get to learn so much science along the way? Math isn't just theorems and proofs. It can also be chemistry, biology, and physics. And coming from someone who loved math in school, I think that applied math is a really great opportunity and it's quite a lot of fun. So thank you. That's a really good question. So in the case of virus modeling, this would happen quite a lot. So even in this graph here, you might notice that the pink line looks like it's going to stay lower than the green predicted line from then on. And this kind of thing can be explained. So we would see then if the actual number of people getting the flu is much less than the predicted, that could be due to things like changing intervention measures or maybe higher rates of vaccination. So the model would have had assumptions based on what the current restrictions were or what the current vaccination levels were. But then as those change, your model has to change. So if you don't change the model, you will see things starting to differ over time. And that's also why for things like virus modeling, we're only doing a 14-day prediction here, because things change so quickly that you can't do a prolonged projection, because there's going to be other things that play into this. And it's also quite important to consider human behavior, because if we're told that so many people are going to get the flu or COVID over the next couple of weeks, people get worried and want to stay home and make sure they don't get sick. So this means the rates of contact in the community are less than the model predicted, which means then the model is going to be wrong because people have changed their behavior, which has changed the contact rate. So you want to make sure that you're taking into account what is really happening. This happens less so with the battery problem, for example, because it's not influenced by behavior. It's, you know the materials and you know what they're supposed to do. So there's not a lot of room for surprise. But when people are involved and psychology and things like this, it does get a lot more complicated. I don't think it actually does. So this is what we're trying to figure out. When these reactions happen, sometimes the lithium is like pulled into a layer almost outside where it's supposed to be, and this layer builds up over time. And sometimes this can cause like cracks to form inside the battery, and this can affect the performance as well. So the size doesn't directly matter, but one of the projects that I'm working on now involves using really, really small wires called nanowires in your battery instead. And some provisional experiments have shown good results with these. So we're investigating it mathematically to see why less lithium gets stuck in these kind of materials. Probably not very conventional. So as I said, I'm not sure if everyone heard my pitch, but my undergrad was in actuarial math, because in school I really liked math, and I thought if you liked math, you went and you did finance or teaching. I realized that wasn't for me because I was missing the other sciences and I wanted to be able to do it all. So I did a master's in mathematical modeling, and this was mostly an applied math master's. So I got a lot of exposure to problems like this during that master's degree. And I was very lucky because one of my supervisors for my master's thesis was interested in these kind of problems. So that's essentially how I've ended up in this area. To be honest, it was completely different. The master's was much more varied. So the topics we covered were very different. I did courses like mathematical geoscience, mathematical biology, and mathematics of natural phenomena. So it was very much based on this type of approach to modeling different things that are happening in the world around us. And that is when I knew this is what I wanted to do. I think overall, it's not on like the students. I think it's on, I suppose, people like me, people who have experienced this, to raise the awareness of these different career options. That is one of the downfalls, I think. No one really knows what you can do with a math degree. And I think it's important that people know you can do all this cool stuff with math. and you are not limited to a particular career. You can go into finance, you can go into the healthcare system. Like, there's really no limit. There's math somewhere in every different area. Busier than normal, for sure. So as an early PhD researcher, I wasn't exactly roped into every single project, but even then, there was quite a shift. For example, one of the courses that I was doing used to cover different topics, but this term it was shifted to just being virus modeling. So I think anyone in the community, anyone who had any skill that could help in any area of science or otherwise, jumped on board to do something. And everyone helped to make a difference. And it's been really, really amazing to see everyone come together like this. Sorry, I think I'm diverting from your question a little bit. So for me, it wasn't the biggest shift in the things that I was doing, but it still was, more time put towards this kind of modeling. For you. So when I alluded to the fact that imagine if our phones could last 1 year. So there is research going on in the battery community to see if we could use nuclear waste to power batteries, in which case our phones could last as long as a year or even longer without being charged, which is quite amazing.